Hello, Yuvraj. Can you hear me? Hello, am I audible? I cannot hear you for some reason. Okay. Yuvraj, could you switch on your video as well? Lovely. So that means you can hear me. So why can I not hear you? हाँ पीछे है पीछे. But even your mic is not moving here also, so I don't think you're receiving input. Maybe it's not. Maybe it is. Maybe it's automatic. Sorry. Yeah. Okay, so let's start. And let's, like always, start with the review. So, what all did we talk about last time? I cannot hear you at all.
Yeah, sorry, sir. Am I
Ah,
audible?
yeah, yeah, yes, you are
Yeah.
audible now. Thank you.
So, sir,
Yes, go ahead, go ahead.
last time we did motion in an electric field, uniform and non-uniform.
We talked about the electric field.
That's the last thing we did.
We talked about motion in electric field, right?
Yes, sir, that was the last topic we got.
Electric field and motion. Okay, so let's continue with that chain of thought. And last time we were
But
talking about.
this wasn't much clear to me. Like, I wasn't able to do the assignments.
Okay.
Like, I don't know why, but
Okay, no problem. We can have a separate session for that. Don't worry.
yes, sir.
Okay. Um, okay. So right now, what we were talking about is we were talking about like a particle, like an electron or a proton, for example, a P positive particle going through an electric field. This was the last thing we talked about, and we realized that a positive particle will go on a parabolic path along the field, and a negatively charged particle will go opposite to the direction of the field in again a parabolic path. How did we know it was a parabolic path? We knew it was a parabolic path because it was a function of a y goes as x squared. So there was a quadratic relationship between the y coordinate and the x coordinate, and hence we knew it was a parabola. Okay, so the final result. Okay. Let me give you a question. Let's say you have an electric field in the upward direction with some magnitude E, let's say, and you have a charged particle. Let's say this charged particle has some mass m and has some charge q. Let's say it has positive charge and it has some charge q. It starts at this point. Let's call this point x is equal to 0, and it starts moving in this direction with some energy which is given to be E. Okay, so the question is how far along. Let's say this whole width is some length 2h, so that half of it is just h, and it starts from the center point, the middle point. So the question is how far does this go and uh, hit the wall? At what distance does it hit the wall? Calculate this r. Does the question make sense?
Yes, sir. So the particle is moving with some energy, and we are taking the displacement, initial displacement at zero.
Yes.
So we have the direction of E, which
Hmm.
acts at 90 degree to the particle,
Hmm.
which is already moving with the energy.
Yes. With some energy E, which you can say is all your kinetic energy, so half mv square. So your symbol for the energy and electric field will be exactly the same. So hmm, let's use for the energy one. Let's use small e. Okay. So we're using small e for the energy because otherwise the symbols will be exactly the same.
So we have the velocity with which the mass is moving, right?
Absolutely.
So we can differentiate that velocity to get the displacement.
Differentiate the velocity. Just
Would
a
that
second.
help?
Huh?
Would that help differentiate the velocity?
Oh, yes, it would help, but what you'll get is as a function of time, right?
Yes, sir.
But you don't want it as a function of time. You want it as a function of the known things, the things like velocity, things like position, are things like the height. So let's do that. Let's write the energy down. So it's E by m. There's a 2 in the numerator and there's a square root here, correct?
Yes, sir.
Okay, so what you said is we can write v as dx over dt, since all the velocity is in the x direction. So this v is essentially vx, and your vy is 0, correct? There's no motion in the y direction initially.
Yes, sir.
uh, okay, so your dx by dt is just square root of 2 e by m. Take the dt on the other side and integrate on both sides. What do you get? You get integral dx. Where do you start? 0. Where do you go to? Well, you're supposed to go up till r. That is what you need to find out. Let's just put it there. And this integral will be square root of 2 e over m, um, dt, from t is equal to 0 to t is equal to some t when it reaches that distance r. Okay.
Yes, sir.
So this implies your r is nothing but, since all of this is constant, this will go out of the integral, and you will only have integral dt. So hence this t, so essentially you just get 2 e over m times t from 0 to t. So this implies r is just square root of 2 e over m times t. Make sense?
1 minute, sir. So what we did was we took the Vx equal to dx upon dt.
Hmm.
Then we transferred the dt over there.
Hmm.
So it came out as root 2 over mt.
Hmm.
And then we directly.
You didn't really have,
Secondly, where did R come from?
from the integral, from the limit of the integral. So it's going from
Oh,
x equal to 0 to x equal to capital R.
so that would become R minus 0. So R there.
you could have written the end statement directly. If you just look at it, what essentially it's saying is that the distance traveled in the x direction is equal to the speed multiplied by the time it takes, right?
Yes.
So you could have just written it as a distance equal to speed into time. So v into t, so vx into t, and vx is just square root of 2e over m from here, right? It's exactly the same thing.
Yes, sir.
Okay. Now, but we still do not know at what time it actually reaches at that point, right? So we still need to calculate this t here. How do we calculate the t? Well, we exploit the motion along the y-axis, and that is how essentially we do that. So we know the initial
What
velocity along the
when will it,
y-axis.
when
Okay, sorry, apologies. Take your time to write this down. Sir.
done, sir.
Lovely. So, okay. So what we essentially got was that R is just V, which is sorry, 2E over M multiplied by the time it takes, correct? And we still need to calculate how much time it takes. Well, for that, let's analyze the y direction motion. You're essentially in the y direction. What is happening? You're starting at a point which is at the center. So you're traveling a distance h, which you already know, and you have an acceleration, you have a force acting on you. This because
Yes.
since there's an electric field in this particular direction. How much is the force? Well, if the electric field is E, then the force would be Q times E, right?
Q times E. Why, sir? Okay.
Yeah,
Huh.
because electric field is defined as force per charge. So that's why. That is how electric field is defined, right? Electric field is defined as the Coulomb's law, a Coulomb's force divided by charge, correct?
Yes, sir.
So hence force is just the charge that is kept in an electric field E. Okay, so if that's the force, this implies your acceleration is mass times acceleration is again your force, Newton's first law. That's what we're using here, Newton's first law. And your acceleration is this means QE over M. So how much time does it take? This acceleration is constant. So you can just use v is equal to u plus 80 if you want. Um, but if you use that, you don't know what your v is, your final velocity is. So the other formula to use would be s equal to ut plus half at square, correct?
Yes, sir.
So for that, you're traveling h distance. So s is just h. Ut, your initial velocity is zero. So you have a zero and plus half a t square. So what's the acceleration? Acceleration is QE over m times t squared. Make sense? I could have
Answer?
I could have taken this equation and written it as dv over dt and then
Yes.
integrated it and then written dv over dt as dx over dt and integrated again, and I would have gotten the same result. But since mm, uh, Newton already gave us these formulas, we don't really need to solve this again and again. We already know what the solution of this equation will be. It will be
Yes,
s
sir.
equal to ut plus half t square. So just substitute the values. What you get, h is equal to half q e over m times t squared. This implies your t is just the square root of 2m over qe. There will be an h in the numerator as well. So this will be the time it takes to reach the top, correct? So let's just take this time
Yes.
and let's just substitute it up here. And that is how you'll be able to calculate how much distance it travels. Sorry, making the same mistakes. So note this down. I'll move on to the next page then.
Done, sir.
Lovely. Okay, so you had two equations. Your first equation was r is equal to square root of 2e over m times t. And the other equation was t is equal to square root of, what was it? There's a lot of things there. There was 2mh over qe.
Ji, sir.
Uh,
Understood.
2mh over qe. Lovely. So,
Understood.
so the distance that you're traveling is going to be 2e over m multiplied by 2mh over qe. Correct? Just
Yes,
substituting
sir.
this inside here. The m cancels out. Lovely. E is the energy, so that's fine. So you have square root of 4eh over qe. Now, what is this thing dependent on? Well, it's dependent on the energy at which you're sending the beam. That makes sense. It's dependent on the electric field. That also makes sense. It's also dependent on the charge, right? So
Yes,
what you can do is you can use this kind of an apparatus in order to separate out particles which have different charges, correct? So essentially, if your goal is to, for example, get oxygen plus, oxygen 2 plus, oxygen 3 plus, and so on and so forth, if that is your goal as an experimenter, what do you have to do? You all you have to do is just take a gas, right? Take a gas of oxygen, heat it up so that you have different combinations. So you have many charged particles here. All the electrons will start leaving. So you will have some concentration of O plus, you will have some concentration of O2 plus, you'll have some concentration of O3 plus, correct? And then what you do is you give all of this some energy, you put it in a particle accelerator and you accelerate it with some energy E. And since the dependence is so strong, it's inversely dependence on the square root. So for just one charge, you'll have E here. For two charge, you'll have 2E. That's 1 over square root 2 times different. So if you'll have one R here, then you'll have R over square root 2 here, then R over 4 here. So you can separate out different charge particles and you can beam them along into different directions for different kinds of experiment. Does that make sense?
so, basically, what we are saying is with the difference in value of Q, we'll observe a change in the value of R, and
Yes.
so we can differentiate the
So
various
it's an
charges.
easy experiment way in order to separate out different ions, correct? Different kinds of ions. So that's where it's essentially used. Um, okay, because you can control the energy of the beam and you can control the electric field very accurately. So you can very accurately get these beams of charged particles, and that is exactly what they use in these particle accelerators as well. Okay, let's move on. Till now we've talked about just particles in an electric field, right? Particles in electric field. Now let's go a step further. Let's make things slightly more complicated. Rather than using a particle, now let's talk about a dipole. So let's think about an electric field. So let's say you have an electric field in this direction, given by some magnitude E. And let's say you have a dipole. Let's say you have a dipole with the negative end kept on the left and the positive end kept on the right, as always. And there's a line that's supposed to join them. Yes. And we already know what the distance between these two is. It's going to be 2a, which is a natural quantity that we use, which is essentially the bond length of this dipole, if you want to think of it like that. And so there's a positive charge here. The positive charge is going to experience a force, which is going to be, if both of them have supposed to have equal charges. So the force that this one is going to feel is going to be q times e, correct? and in the
Yes.
positive I direction, and the negative one will experience the same force but in the opposite direction.
Negative I direction.
Yes, in the negative I direction. So if we just talk about translation, if we just talk about motion in XYZ, so if we talk about just translations, the net force on this box is absolutely zero, right? So you have so your net force F net is just equal to QE I cap plus QE minus I cap, which essentially cancels out with each other and gives you zero, correct? So your net force is going to be zero. So the dipole, the center of mass of the dipole is not going to move. Does that make sense?
So the center of dipole is does not makes the difference.
The center of the dipole is not going to move
Yes, sir.
because there's no net force
There's no net
along
force.
along
Equal
the x
force.
direction.
Yes, sir.
Lovely. But however, there is going to be a torque. There is going to be a torque that is what this dipole is essentially going
So
to move.
that's what I was thinking that the thing would rotate because
Yes,
it's
exactly. So why
based
is it going to rotate? Because what
so
you
the
essentially
force is
have.
not acting perpendicularly or in symmetry. Force is acting at a certain angle.
Yes. So the force is acting here. So we can always. So let's say the dipole was or at an angle theta with the electric field. So we can always divide the force into its components, right? So we have the force here. We have, if this is theta, then this is going to be theta, because parallel lines and line intersecting them, and so this component would be f cos theta, because you're going towards theta. This component is always going to be f cos theta, and the perpendicular component is going to be f sine theta. And here also you'll have an f. So here the angle, this angle is theta. So if I increase this along, so this angle would be theta, and this would turn out to be f cos theta, hence, because you're going towards the theta, and in this direction it will be f sine theta again. So what you see is the f cos theta and f cos theta both cancel out. So along the dipole, what is happening? What is happening is the forces cancel out. Forces cancel out. Meaning F, let's say along the net force along net. Um, this is going to be uh, F cos theta minus F cos theta. So that's going to be zero. But what about the perpendicular components? Well, the perpendicular components, what they're going to do is they're going to apply exactly this torque. And what is the torque on a system given by? It's given by R cross F, right?
R cross F.
Yes. What
And
is
so
it?
R is
R is the distance from the center of rotation,
oh, okay. Anji sir.
right?
R cross F.
Yes. So in this case, how much is R?
Sir, R is equal to A.
Yes, R is just A. And what is the F that is acting?
Sir, F is equal to
The force
F
that is
cos theta.
F cos theta. F cos theta is in the direction along with the
No,
dipole
F
moment.
sin theta. F sin theta.
F sine theta, but there are two F sine thetas, right?
Yes, sir.
So it will
So
be,
both will add up because they
yes,
are acting in the opposite direction.
or at, yes. So it's along the same. It's trying to rotate the body in the same direction. So both of them
Yes,
are trying to essentially rotate the body clockwise, right? So
yes,
both
sir.
of
So
them are
they
trying to rotate the body clockwise. That's why they add up.
to 2F sin theta.
Yes. So this becomes 2f sine theta, and f is just q times
E.
sine theta, which makes sense also. So you have 2aqe sine theta. And if you do, you remember this 2aq, this quantity that we had defined, which was the dipole moment, right? Yes, the moment, the electric dipole moment. And we had denoted it by p. So this is pe sine theta, or we can also write it as p cross. Does this make sense?
Yes, sir.
So for a dipole in an electric field,
So torque is defined by Z.
this is not z, this is tau, t, Greek letter for t, tau. So for a dipole in an electric field at a given angle theta, the net torque that the dipole with dipole moment p is going to face is going to be p cross e. That is essentially the result we have here. Now, what about the direction? How do you figure out the direction when you have a cross?
So if it's clockwise or anti-clockwise,
So in this case, what direction will the torque be?
so torque will be in the clockwise direction.
Yes. So when you say clockwise direction, so torque is not in the clockwise. Yes, the force is in the clockwise direction. The torque is R cross F. So it's going to be R cross F. So it's going to be inside, right? So you have to use the right hand thumb rule, correct?
Yes, sir.
So put your hand along the first vector and you rotate along the second vector, and your thumb essentially gives you the direction of where the torque is going to be. So if you do this here, your R is along this direction, along the P direction essentially, and your F or the force is outside, so it will go down. So the torque will essentially be inside. Or you can also see it like a screwdriver, right? So if you have a screwdriver, if you're rotating it clockwise, then it's going inside, and if you're rotating it counterclockwise, it's coming outside. So it's exactly the same thing. It's exactly the same idea. So the torque is inside because it's going in. Does that make sense?
Yes, sir.
Lovely. Now, now, what happens if the dipole is perfectly aligned along along the direction of the electric field? So let's say you have an electric field here, and you have a dipole which has the negative end here and the positive end here. So it's perfectly along the electric field. Well, the net torque on this system is going to be zero, right?
Yes, sir.
And the net force on this system is also going to be zero.
Zero.
So hence, this is a point of equilibrium.
Yes, sir.
And so is the other way around. When you have the plus here and the minus here, this is also a point of equilibrium, correct?
Yes, sir.
Now, is what is the difference between the two points, between
So
this
between
state
the
and this
two,
state?
so that the
Both,
charges are flowing in other opposite directions.
yeah, the charges are in opposite direction. So what does that do? See,
So
if
that means that the electric field will be in the opposite direction.
no, wait. So think about it. So you have the positive charge here. Let's move this slightly, okay? Let's move this slightly. Let's move it at an angle side. Since this is plus, this will keep on moving here. This is minus, this is moving here. So what will it do? It will restore it to the original position, correct?
Oh, 1 minute, sir. So I guess the upper one will eventually move in the clockwise direction and lower one in the anti-clockwise direction.
Lower one would move. So wait, listen. So the first one, if you move slightly, it's going to come back to the original position, right? So it's like a system, which is it's like a ball, which is kept inside a cup. So if you move it slightly, it will come back after some time to the original position. After obviously doing some oscillations, and it will come back to the center position. Exactly, this thing is doing here. It will oscillate for some time. It will come back to the original position. Correct. This is
Yes,
what
sir.
is called a stable equilibrium, right?
Yes, sir.
But think about the other part. Let's move it slightly. Let's move it slightly.
So this will move the whole,
Yes,
it does
since this
move
is
whole.
negative, the force will be this side. Since this is positive, the force will be this side. So the thing will start moving until unless you come back to the original position.
Yes, sir.
So you come back, so this will rotate completely. So this plus minus will become minus plus. So this is like a situation where you have the ball on the top of an inverted cup. If you move it slightly, it starts falling down, it starts moving and goes to another equilibrium point. So this is what is called an unstable equilibrium.
Yes, sir.
Now, why is this happening? Why is one condition stable and the other condition unstable? Well, the answer to that will come when we're talking about the energy that is stored in the system. And we'll come to that in some time. But before that, let's do a couple of questions on exactly this concept. So let's say you have the electric field. Oh, why am I doing so dumb? Sorry. Yes. So, question. Show that the dipole, show that the dipole in an electric field, oscillates harmonically. Harmonically, which also means SHM. It's doing SHM, essentially. Oscillates harmonically. Full stop. Sorry. So essentially, what you have is you have an electric field and you have a dipole which is kept. And what will essentially happen is if you move it slightly, as I said, it's going to have some restoring force, and what that restoring force will do, it will restore it towards the original position, but it will go back and it will outstretch, it will go back to the other extremum, and then it will come back, because at some point the opposite force it becomes stronger, so it will come back and it will keep on oscillating. The question is that prove that this oscillation is actually simple harmonic in nature. So
So
go ahead.
simple harmonic में क्या होता था?
I'm sorry.
So simple harmonic में क्या होता था?
What does it mean for a motion to be simple harmonic? Okay.
फिर करा था लास्ट ईयर याद नहीं आ रहा.
Okay, so for simple harmonic motion, what you essentially need is that your force is proportional to x, or to your displacement.
Yes, sir.
So your displacement can be in x also, but it also can be in theta, right? So in this case, the displacement will be in theta. Go ahead.
1 minute, so I'm trying.
I'm sorry. Take your time. It's slightly hard, slightly technical question. Just give me a second. I just go grab a cup of water, okay? Yes, thoughts.
सर इसको शो करने का सर एक तरीका ये हो सकता है क्योंकि फोर्स जो है वो डिस्प्लेसमेंट के प्रोपोर्शनल है,
Hmm.
तो जो हमारी फोर्स एक्ट करेगी वो इलेक्ट्रिक फील्ड के तरह ही तरफ ही एक्ट करेगी जो करेगी ऑब्वियसली, और वो क्या कहते हैं उसका जो व्हाट यू से साइन थीटा वाला वेक्टर होगा, वो इवेंचुअली जितना हम उसे व्हाट यू से
छोटा करेंगे।
बढ़ाते रहेंगे थीटा को, उतना वो भी बढ़ता रहेगा। सो
ओके।
उससे ये प्रूव कर सकते हैं कि इट्स प्रोपोर्शनल टू थीटा।
Okay, so there is a difference between. So you said it is proportional. Yeah. So there's a difference. So you cannot prove that it's proportional to theta from there, because what you at the end of the day prove, it's proportional to sine theta, and sine theta is not theta. Yes, both are monotonically increasing function, but they are not equal. You know why? Because sine theta can be written as theta plus theta cube over 3 factorial, actually minus theta cube over 3 factorial plus theta 5 over 5 factorial, minus dot dot dot. So it's an infinite series of a lot of powers of theta. So you have higher order powers as well. It's not only theta. Yes, the leading term is theta. The first term is theta. That is absolutely true. But there are higher order terms as well, and these higher order terms will is what is going to become problematic. But things are not that problematic actually, because you can actually ignore these higher order terms. When can you ignore these higher order terms? You can ignore these higher order terms when theta is really small, right? If theta is
Yes,
really small, then theta cube is obviously way smaller than theta, and theta to the power 5 is also going to be way smaller than that.
so they can be neglected.
So all of them can be neglected. So let's do that. So that's a good idea. So let's take the torque that we had. Since we're talking about thetas, so let's start with the torque. And torque we've already calculated to be Pe times sine theta, correct? And let's
Yes, sir.
work with the small theta approximation. Sine theta. So let's say theta is very smaller than 1 radian, that is. So sine theta is approximately equal to theta, so we can write this as Pe theta, correct? Now now what essentially you are saying is that your torque is proportional to theta, because both of these things, your electric field and your P, which is the moment, both are constants, correct? So now what you're saying is your torque is just proportional to theta, and that is exactly what you had to prove. So hence proved. Yes. So your torque is proportional to theta. Yes, it's exhibiting simple harmonic motion. What next? Now go ahead and calculate or find the time period of this oscillation. Okay.
Yes, sir.
You know what this is called?
No, sir.
So every function, any function you have, can be expanded using many series expansions. These are what are called series expansions. There are many kinds of series expansions. There is Taylor expansion. There is Maclaurin series expansion. There are many others. But power series expansion, I think what they've used is power series expansion. Most of these
तो
are
ये
power
काम
series.
कहाँ आती है वैसे?
Huh?
सो ये और कहाँ पे काम आएगी एक्सपेंशन अगर रन हो?
हर जगह काम आएगी. Yeah, this is essentially what physics is based on. uh, it's essentially telling you how you can take a function and break it down into its constituents. So if you think about it, then what essentially you're doing, you're taking theta and dividing it into how the linear terms works, how the quadratic term is zero, क्योंकि इसका ऐसा you can imagine it as theta plus 0 times theta square plus or a minus, sorry, a plus minus 1 by 3 factorial times theta cube plus 0 times theta 4 plus dot dot dot. So it's again like a power series kind of a thing, right? So it's a series of powers, and uske aage uska coefficients hai. So you'll see this kind of expansions a lot in the future, and especially if you're studying with me, I do these expansions quite a lot because they're very useful and very important. Okay, so the time period.
सर For the time period, what we can do is
हाँ जी.
that we can, what do you say, differentiate the displacement
uh,
with respect to time.
the wait, differentiate the displacement with respect to time.
So what that does is it gives the number of the
Do you really
displacement in
have to do that?
uh, the time period is basically number of oscillations in 1 second, right?
uh, yes. So you are saying you calculate the velocity and from there you calculate how much. That's a very very long process to do it. There is a direct way of doing it. Okay, let's think about this. Very very simple. Let's move on to the new page, to a new page. Okay, because things are getting very clustered here. So you have this situation where you have a positive charge and a negative charge, which are at some angle, small angle theta, uh, with the horizontal, and essentially the system is left there in an electric field, and the point is that it will experience some torque, which is essentially going to be Pe sine theta. And we said that theta is small, so this is just going to be Pe theta. But this is slightly wrong. This is slightly wrong. There is one thing that is wrong here, which is essentially the direction. Because since it's a restoring force, remember, right? So in a restoring force, you always put a minus sign. For example, in a
Why, sir?
spring, for example, in a spring, you put a minus kx, right? Force.
Yes, sir.
Because it's a restoring force. But not only that, think about it. What direction is the torque in? The torque is in the inside of the plane,
Talk
right?
to
It will be inside the plane because
Yes,
uh,
sir. Talk to
because it's P cross E. P is in this direction. E is in this direction. So you take this direction, and if you want to cross them, it will always be in the plane perpendicular to it. The first vector cross the second vector, and the thumb will give you. So it will be inside the plane. So I'll put a dot for inside. Sorry, I'll put a cross for inside and a dot for outside the plane. So this is
सर
essentially
आपकी वीडियो चल रही है?
मेरी वीडियो चल रही है as in?
Like, have you turned on the video?
No, sorry. Apologies. I just realized. Sorry.
नहीं
Yes.
सर, मुझे इसमें वैसे भी नहीं दिख रही cause I don't know, I joined from the Learnivio website, तो even I have turned on, तो मुझे अपनी शक्ल भी नहीं दिख रही, आपकी भी नहीं दिख रही, तो मुझे ऐसे thumb rule समझ नहीं आ रहा कैसे करना है।
Oh, okay. Can you see me अभी?
सर मेरे को ना Zoom से ज्वाइन करना पड़ेगा cause इस पे आती है दिक्कत जो Learnivio की वेबसाइट है।
Okay. Okay, that is problematic. It's super
यस सर, ये मैंने
problematic.
बहुत बार नोट किया है।
Okay, so we can. How can we do this?
सर निष्कर्ष सर है आपके आसपास?
हाँ है. एक मिनट, just give me a second. सर वैसे इस बच्चे को वीडियो नहीं दिख रही है. हाँ, ना उसको अपनी दिख रही है. वीडियो नहीं दिख रही. ना मेरी दिख रही है, ना उसको अपनी दिख रही है. हाँ, वाइट बोर्ड दिख रहा है. हाँ जी.
निष्कर्ष सर मेरे को Zoom की लिंक भेज दो प्लीज।
क्या हुआ, फिर इशू आ रहा है इसमें? तो एक काम
पर
करो,
इसमें वो नहीं चल रही, वीडियो नहीं चल रही।
अच्छा एक काम करो, लॉग आउट करो, मतलब लीव करो, नीचे लिखा होगा ज्वाइन ऑन जूम, उस पर क्लिक कर दो, जूम से कनेक्ट होगा।
ओके सर।
So you could have guided him with.
I don't know what all this is.
मैं तुम्हारी वीडियो देखी, बाकी सब देखी।
उसको अपनी वीडियो बनी लगी.
Which is fine.
हाँ.
You can't see your video.
Hmm?
Even you can't see your video.
I guess.
Okay. ये तुमने वीडियो ऑन नहीं करने की स्मार्ट लगा।
मेरा तो वीडियो आ रहा है.
ज्वाइन कर पाएगा वापस ज्वाइन। फोन
Join and Zoom only works on laptops, as they should.
I remember. लैपटॉप पे बैठे थे जहाँ तक मुझे लग रहा है. क्या सोच रहे हो सर?
नहीं लैपटॉप ही लेता हूँ.
लैपटॉप से
हाँ निकाल लो बताओ ना वो बटन.
हाँ
100 बटन काम नहीं कर रहा हूँ. ऐसा कुछ हुआ? My details. अच्छा तो अच्छा है.
अच्छा चुप करेगा
भाई वो.
Ajay, can you see me now? Hello. Can you see me? I cannot hear you.
Yes, sir.
Okay, I can hear you now. Lovely. So yes.
So now I can see your video. Yes, sir.
Why is this DJ? I don't know how this works. Okay, whatever. Yes. Okay, so yes, the direction of the torque. The two vectors that essentially we need to care about when we talk about the direction of the torque is the p vector and the e vector, right? We figured out it to be p cross e or the r cross f. It's exactly the same thing because r is going to be in the direction of p and the f is also going to be in the direction of e. So the direction from there and direction from r is going, obviously has to be equal also, and we can see it's going to be equal as well. So how do you use the thumb rule? You take your hand, you put it in the direction of the first vector. In this case, the p vector is, let's say, along my hand. Uh, the e vector, let's say, is in the direction of my thumb. Okay, so it's in this direction, right? In this case, since your p is up here, this is your p vector, and this is your e vector.
Yes, sir.
So what you have to do is you have to rotate your fingers in the direction of E. So just completely rotate them नीचे. और जो thumb होगा, thumb का direction जो है, that is your vector. So in this case, it's here, so it will be inside the plane, right?
So, sir, this is the suppose the p vector acts in this direction
Yes.
over here, and e vector is in suppose this direction.
Yes, thumb वाले direction में. So rotate your hand नीचे, and now your thumb
So
straight
that
out.
so it would go inwards.
Inwards, yes, absolutely. Now let's try to do the opposite also. If your electric field was, let's say, ऊपर, so तुमको ऊपर की तरफ घुमाना पड़ेगा,
जो कि outwards हो गया.
जो कि outward आ जाएगा. Make sense? So
Yes,
सारा क्रॉस प्रोडक्ट ऐसे ही काम करता है. कहीं भी तुम क्रॉस प्रोडक्ट देखोगे यही करोगे. पहला वेक्टर दूसरा वेक्टर घुमा दो. The end. Now and then you will start noticing pattern also. So first pattern to note
yes.
is
So मतलब
essentially,
इसके 3D में imagine करना है इसे.
yes. Now, so essentially the point to note is whatever plane the two vectors are going to be in, the cross product will always be in the plane out of that, right? या तो out of that in this way or out of that in this way. It can be have two possibilities, right?
Yes, sir.
So it can कोई भी plane में कहीं पे भी है, या तो अंदर होगा या बाहर होगा, right? और कोई ऑप्शन ही नहीं. So अंदर कैसे
Yes, sir.
होगा? So just remember it. If it's clockwise, it's going to go inside. If it's anti-clockwise, it's going to go outside. That's it. Okay, lovely. So that is why there's a negative sign here since it's a distorted force, and we figured out that this can be approximately written as PE theta. Lovely. So now,
मैं तो
Now my torque is given by I times alpha, right? Newton's equation. Yuvraj, are you there?
Yeah, sorry, sir. Someone just walked in.
Oh no, no. So okay, so your torque is given by I times alpha, which is your moment of inertia multiplied by your angular acceleration, right? This should be equal to PE times theta. Okay, so now your alpha, which is angular acceleration, is actually equal to d omega by dt, which is actually equal to nothing but d2 theta over dt squared, correct?
1 minute, sir. I need to.
Okay, okay. Sorry.
Sir, how did we take talk as IL?
It's exactly when you would have studied circular motion. So your force is mass times acceleration. Your torque is I times alpha, right? So I is your moment of inertia, and alpha is your angular acceleration. So it's essentially Newton's law for rotation motion. Exactly the same thing. Does that
सर
make
क्रैश
sense?
कोर्स करना पड़ेगा लग रहा
कर लो.
है.
So we can actually sit and ये छोटे छोटे जो problem है, we can actually talk about these if you want. It's absolutely fine. Also, I forgot the minus sign also. Okay.
So, first we differentiated W. W was
W, it's omega. It's not W. It's angular velocity. So V is equal to R cross omega, right? Remember this?
yes, sir.
So it's essentially that omega.
And so Q is something for distance, if I'm not wrong.
Yes, for angle. Theta is angle.
Oh, it's theta. Okay.
Always remember when we're going to talk about linear motion or translations, okay, things are moving from A to B, khali translating, we're going to use Roman alphabets. So we're going to use A, B, C, D, or V for velocity and X for distance. And whenever we're going to talk about rotational motion, we're going to use Greek letters, alpha, beta, gamma. Okay. So hence I've used theta here, omega here, and alpha here. Does that make sense?
Yes, sir.
Lovely. Okay, so since we already know how to write alpha, let's write alpha. This is d2 theta over dt squared is equal to minus pe theta. Well, let's simplify this further. This differential equation seems to be very familiar. It's essentially the equation of a simple harmonic motion. I've done it again. Sorry, just okay. Let me know when you're done. Uh,
Yes, sir. Done.
Lovely. So, your I times d2q over dt squared is equal to minus pe times theta, right? So let's take this I on the other side also. d2 theta over dt squared is equal to minus pe over I times theta. Now, notice everything inside this is a constant, right?
Sir, कहाँ पे? Like,
No, inside the brackets. Inside the
so I'm not
brackets,
able to see where you have written the thing.
as in,
Sir, have you written anything right now?
yes.
So I'm not able to see it on the screen.
What?
Yeah, whatever you just wrote, I'm not able to see it. Like, it's not on the
Now I'm
screen.
scribbling on the screen. Can you see any of this?
No, sir. Legit nothing. Wait, I'll just send a photo to Niskar,
No,
sir.
no, no. Yeah, do that.
सर ये तो स्कैम हो गया। सब भेज दी मैंने।
Nice. I'm trying a new page. Is it working here? Ah, okay. Wait. Now yeah, you're able to see.
Yeah, now I'm able to see the strip.
Nice. Ha. Makes sense. Makes sense.
हाँ सर अब दिख गया।
Okay. So what I had written was I times t2 theta over dt squared is equal to minus pe times theta, which is exactly the same as the previous page. And all I did was I took the moment of inertia, which is I in this case, and brought it in the denominator on the other side. So now what you have is d2 theta over dt squared. So all the derivatives on one side and the function on the other side. And what I said was notice that everything inside the bracket, the moment of inertia, the electric field, and the moment of inertia is Nietzsche, the dipole moment or the electric dipole moment, which is P, all of them are constants. So this whole term is going to be a constant, right?
Yes.
So let's call this constant some k times theta. Now, does this equation look very familiar?
1 minute, sir. This is the differential of x. Oh, so differential of.
Yes, this is exactly simple harmonic motion, because
Yes, sir.
if I just put theta here, theta is x here, this is just d2 x over dt square, which is acceleration, is equal to minus k times x. That's exactly the same thing. So we know that this is simple harmonic motion. So this so simple harmonic motion का equation क्या होता था? उसका होता था d2 x over dt square is equal to k over m minus k over m times theta. And we used to say that omega is equal to square root k over m. Remember all of that?
Yes.
Remember all of that? So
Ji, sir.
so this is essentially omega square. So minus omega square theta. So essentially meaning this is x. This is not theta. This is x. Essentially meaning that all of this inside the bracket is just your omega squared. So if just comparing these two equations, everything in this inside this is omega squared. So everything inside this is also omega squared. And that is exactly what you do. Essentially, what you found out is the frequency of rotation, right? So omega
Oh,
square
yes,
is
sir.
PE over I. Now, since you found out the frequency, you can find out the time period also, because time period is just the inverse of the frequency, right?
Yes, sir.
Uh,
So it will be I upon PE.
just a second. So नहीं अभी तो square root of PE over I,
P over yes, sir.
and time period is 2 pi over omega, which is 2 pi square root of I over P times E. So this is essentially the time
Hmm.
period of oscillation of an electric dipole in an electric field.
So why did 2 pi come here?
That's how you define time period. So it's essentially to do with how you define this omega. So omega and nu, these are two frequencies you must have heard. Nu jo hoti hai, that is cycles per second. So this is cycles per second, and this omega is actually radians per second. So ये जो एक साइकिल, एक पूरा सर्कल खत्म करने में कितना रेडियन होता है? 2 पाई, राइट? सो योर न्यू
Yes, sir.
इज जस्ट 2 पाई ओमेगा. यहां से आता है वो 2 पाई. मेक सेंस?
Yes, sir.
Lovely. So this is the time period for this thing. Now you can
1 minute.
calculate the I as well, the moment of inertia of this system.
Ji, sir.
You can calculate the moment of inertia of the system also. How do you calculate moment of inertia of a system? Let's say this is a very simple system. It just has two masses. Let's say the center is at 0. You have two mass m and m दोनों का चार्ज था. इसका moment of inertia कितना होता है अगर point यहाँ पे है? So your moment of inertia is going to be mr squared, right? So m, since it's a point particle, so m a squared plus the for the other one m a squared, which is nothing but 2m a squared. I can put the value of these two things in the time period equation, and what you get I is 2ma squared over I over p, I over pe, which is 2ma squared over p is also equal to 2 times q times a times e. So one of the a's also cancel out and the 2's also cancel out. So I can just write this as 2 pi over ma over qe. So this is in terms of all the natural quantities, so all the physical quantities in terms of the charge, in terms of the electric field, in terms of the bond length, or a or in terms of the mass. So these are the fundamental quantities in terms of which I've written. And this here, yeah, so when I had written time period is equal to 2 pi square root of I over pe. This I've written in terms of more complicated quantities, or more simplified way I've written this. So okay, let's move on. Now this was a magnetic field. Sorry, this was a dipole, electric dipole in a uniform electric field. Now let's talk about an electric dipole. Make things slightly more complicated. Electric dipole in a non-uniform electric field. Well, if the electric field is non-uniform, things become slightly complicated, right? Because now, uh, obviously, there will be rotation, but will the rotate? Sorry, there will be oscillations, but will the oscillation be simple harmonic A? Are the oscillations SHM? Question mark. And what about translation itself? Will it just stay at the same place or not? Translation. So let's say you have an electric field, which is something like this, and this electric field is function of x, let's say. And you have a dipole as always, which is kept at these 2 points here, at distance 2a away from each other, the center point being here, and a minus charge and a plus charge. Now, if the electric field is non-uniform, then the force that is acting at this point and the force that is acting on this point is actually going to be different, right? Because this q times e, this is a function of x, so it's actually dependent on where the thing is. And this force q times e as a function of x is different because both of their x's are different, both of their positions are different, and hence the forces are different. So the net force, actually, when you calculate the f net, it's not going to be zero. So
So
you have,
because E is different for both of them.
yeah, because both of them are placed at different places, and the electric field is a function of space. तो अलग अलग पॉइंट पे अलग अलग इलेक्ट्रिक फील्ड है, तो दोनों को अलग अलग फोर्सेस पता लगेगा, तो इसलिए नेट फोर्स अलग होगा. मेक सेंस? So translation we've already answered. It's absolutely going to translate since the net force is not equal to zero. What about rotation?
So rotation,
Sorry,
what do you
yeah,
say?
oscillation. So let's do one.
Oscillation, no?
Yeah,
Oscillation will be clockwise only.
will be clockwise only, but will the oscillation be simple harmonic in nature? So will you have a force or a torque being proportional to minus x or minus theta? Will that be true
Uh,
for small theta and small x, obviously?
no, sir.
Why do you say so?
Because it will experience different forces at different ends. So
Absolutely.
theta, the relation with theta is not satisfied.
Absolutely. So what we used, okay, let's actually do this also. Okay, let's break this down into its components. So you have, let's say, F1 force here and F2 force here. So this becomes F1 sine theta, and this becomes F1 cos theta, and this is F2 cos theta, and this is F1 sine theta. So first of all, we're seeing that along the axis, we actually have a force. So either the system will essentially, the electric field is trying to bring the system closer or away from each other, right? It's either of the two, depending on how the function is exactly. So
Yes,
F
sir.
along is essentially going to be F1 minus F2 cos theta, right? So this F1, let's write this down. This is QE at x1 minus QE at x2 times cos theta. So it's either going apart and it's coming, or it's coming inside. So this is that motion. And what about F perpendicular? Well, the net torque in the perpendicular direction, what you'll have is a torque, and the net torque will essentially be the sum of these two torques, which is essentially just A times F1 sine theta plus A times F2 sine theta. So here what you have? You have AF1 plus AF2 sine theta. And huh, yes. Okay. So now these two F's that you have, F1 and F2, if you actually think about them, since the electric field are a function of X, your F1 and F2 are also functions of X, right? Yes, no, maybe.
Sir, F1 and F2,
Uh, are also functions of X.
function of X.
X as in this point in space. Let's say this point in space is X, or any point in space. Since I said that the electric field
Uh,
is dependent on X
yes, sir.
or the
They
point in,
they are, sir. Yes,
yes.
sir. They
So
are.
the forces are also dependent on X. That means that the
Yes, sir.
forces are also dependent on theta.
Yes, sir.
अब
हाँ.
जहाँ पे x है, x अगर यहाँ पे है तो थीटा कुछ और है, अगर x यहाँ पे है तो थीटा कुछ और है, right?
जी, sir.
So they are also dependent on theta. So your total dependence on theta, yes, there is a sine theta here, which actually for small theta will go to theta. But how your this thing, your AF1 plus AF2 depend on theta will actually define whether the system will be simple harmonic or not. And since you will get a function of theta here, so and you had a theta here also, so essentially what is happening is you have a function of theta and you have a theta here, so the whole thing is actually a minimum function of theta square, right? Because
समझ नहीं आया sir ये वाला.
okay, so I am proving and trying to prove that my in a non-uniform electric field, my dipole will for sure not do simple harmonic motion. How do I prove that?
हाँ.
By
Yes, sir.
by taking the torque. I take the torque. The total torque is the sum of the two forces or the sum of the two torques. What I do is take the sine theta common, and what I say is that yes, the sine theta is a function of theta, but my AF1 and AF2 are also functions of theta because they're
Yes,
functions of
sir.
X. And
Yes, sir.
so my total torque is some function of theta multiplied by theta.
हाँ.
So this is going as theta squared
Yes,
minimum,
sir.
because इसका minimum जो होगा वो theta होगा, theta plus theta
वो
square plus
थीटा होगा.
theta cube ऐसे तो करोगे ना
Yes,
इसको
sir.
expand. So minimum जो
हाँ
होगा
जी,
वो
हाँ
theta
जी.
होगा, so इसका जो होगा theta
Yes,
square
sir.
होगा minimum. So that is why this
जी,
will
sir.
never be SHM, because the minimum torque will actually be of the order theta square. So that is essentially, this is not in your syllabus, but this is a technique of essentially showing how things can be, you can prove things to be non-simple harmonic motion also.
सर एक क्वेश्चन पूछूं आपसे.
Yes, please go ahead.
सर आप रिलेट कैसे कर लेते हो इतना कुछ एक साथ?
दुनिया गोल है भाई.
हाँ जी सर.
Yeah, दुनिया गोल है. I've been doing this for like forever now, right?
सर दुनिया गोल होती है, मतलब नॉर्थ साउथ नॉर्थ पोल और साउथ पोल थोड़ी ना जोड़ सकते हो, लेकिन सर वो तो मतलब कैसे रिलेट कैसे कर लेते हो इतना कुछ एक साथ? तो कुछ टेक्निक तो होगी ना, मतलब जब आप सोचते होगे तो सोचने से पहले कुछ वो भी करते होगे।
Interesting question. I'll think about that and we'll get back to you. I don't know the answer to that. Anywho.
मेरा मतलब सोचने से पहले सर कुछ आपके मन में आता होगा ना कि अच्छा ये ऐसे है तो इसका ये होगा वो होगा, मतलब थोड़ा थिंकिंग प्रोसेस समझाना सर अपना, मैं भी उसको फॉलो करूंगा।
We can talk about this आराम से in detail at a later point, I'm
जी
sure.
सर।
Okay, so let's do one simple question on this. Um, okay, so the question goes as follows. Plus. In a region of space, so you have in a region of space, you have an electric field which is given by E. E field, the electric field along the Z direction, the electric field is along the Z axis, let's just say the Z direction, the magnitude of the field increases uniformly. The magnitude of the field increases uniformly along the positive to direction, the positive Z direction, sorry, क्या कुछ बोल रहा हूँ मैं? At the rate of 10 to the power 5 Newton per centimeter. न्यूटन पर सेंटीमीटर पर कूलम भी होगा वैसे यहाँ पे, राइट, यस। ओ सॉरी, न्यूटन पर कूलम मीटर होगा ये। Let me write the units down again. Newton meter inverse coulomb inverse, that's a better way of writing it. And then what are the torque and force experience? So the question is, what are the torque and force experienced by a system having a dipole moment as 10 to the power minus 7 coulomb meter in the z direction, in the negative z direction. Okay, go ahead.
एक्सक्यूज मी सर।
Yes, go ahead.
एक मिनट सर।
Uh-huh. Any problem with the question?
No sir, it was something just popped in on my computer.
Uh,
Yes sir. Sir, what is this 10 raised to power 5 Newton meter minus 1 Coulomb minus 1? Why is this thing given? Like, what is this?
So this is the variation of the electric field with Z. The magnitude of
So
field
that is
increases.
at the rate.
Yes, at the rate.
So
Essentially,
this is the variation along the Z axis.
yes. So essentially, what does the statement give you? It essentially gives you how the E is changing with Z, right? So it's just dE over dZ is equal to 10 to the power 5. That's how you interpret this essentially. Okay, thoughts. Just a
So
minute
what
left.
I have
Hmm.
thought is that the as the question says, the electric field constantly increases as we move towards the positive Z direction.
Yes. So you have the electric field in the upward direction, and it's essentially
Yes, sir.
you're given that dE by dZ is equal to 10 to the power 5. Let's call this some constant C, right? Let's call this.
Yes, sir.
So dE by dZ is given to be some C. This implies E is some CZ, right? CZ plus C naught. So let's say at Z is equal to 0, E is equal to 0. So E is just some CZ. Uh, okay. So about the force, how is the situation given? The situation is given
So it is
that
given
the
that
dipole moment
we
is in
have
the negative Z direction, right?
negative Z
So
direction.
that
Yes,
means the
sir.
negative is up and the positive is down. That is what it means, right?
जी sir.
So is ताकि negative plus जाएगा तो नीचे की तरफ जाएगा dipole moment. Lovely. So we already know how far apart they are. They're 2a distance apart. Let's say that um, we need to calculate the total force on this. So, actually, we don't really need to do that. Also, that's brilliant. That's brilliant. Okay, so look here, look here. This is a simple way of doing this. So now, this is a dE by dZ is equal to 10 to the power 5, right? Let's just multiply by Q on both sides. dE over dZ is equal to 10 to the power 5 multiplied by Q, correct?
Q.
Now, Q is the charge, right? Plus Q and minus Q. क्योंकि DE है and Q is a constant, मैं इसको D के अंदर ले जा सकता हूँ. So I can write it as D times QE over DZ is equal to Q times 10 to the power 5, correct?
Yes, sir.
And QE क्या है? Force. So what does this tell you? That dF over dZ is equal to Q times 10 raised to the power 5. And now you need to find out the net force. Lovely. So force हमको पता है as Z कैसे चेंज कर रही है. तो और ये दो जो forces हैं, ये दो जो particle हैं, वो 2a distance अलग है. It's brilliant. So let's say that this is at some Z is equal to 0 and this is at Z is equal to 2a. Okay. Mm, so the net force. So if we take to the it to the other side, you have 10 to the power 5 multiplied by dz. Let's integrate on both sides. You're integrating z from 0 to 2a, and you're integrating the force from 0 to f. And what essentially do you have remaining? So the net force, you have the net force be equal to Q times 2a times 10 to the power 5, right? And q
Yes,
times
sir.
2a you already know is p into 10 to the power 5, and that is given to you. That is given to you to be how much? 10 to the power minus 7, right? So this is 10 to the power minus 7 multiplied by 10 to the power 5. So the net force is just going to be 10 to the power minus 2 newtons. Make sense?
Yes,
And
sir.
since we already know that it is anti-parallel, so in the sense that the magnetic moment is in the downward direction and the electric field is in the upward direction, so it is anti-parallel to each other. We already know what the torque is going to be. The torque is going to be zero because we've already solved this problem before, right? It's
Yes,
an
sir.
unstable equilibrium that this system is in, but it is in an equilibrium, and hence the torque is going to be zero.
So these are all the derivations that we are doing, right?
This is a problem. उससे पहले जो था सारा derivation था.
Yes, sir. This is the problem.
Yes, we are doing all the derivations. Yes. We're not skipping anything. Don't worry.
Huh?
We won't skip anything. Don't worry.
Yes, sir. So we won't skip anything, but वो फिर डेरिवेशन के चक्कर में इतना मुश्किल लगता है कि वो समझते हैं कि वो समझ लेता है कि हुआ ही नहीं है, याद ही नहीं हुआ.
अरे याद नहीं करना है ना डेरिवेशन. तो जब भी याद करने जाओगे नहीं होगा. कभी नहीं होगा वो.
वही सर, मतलब उसको स्टेप्स जो होते हैं एक के बाद एक कैसे करना है, वो डेरिवेशन थोड़ा टाइम लगता है समझने में.
हाँ, वो obviously टाइम तो लगेगा. टाइम लगेगा उसमें. Don't be stressed about the time it takes. It takes time. Everybody takes time. It's a hard problem. It's not that easy. Chalo,
डन सर.
I think we should stop here because it's already 5 minutes past our time, and other people will
यस
be
सर.
waiting. So